Welcome back everyone to our second module on speed accuracy trade-offs, and more specifically today we're going to focus on Schmidt's law. So last module we learned about Fitts' law, named after Professor Fitts, and that was a logarithmic speed accuracy trade-off. Today we're going to see a linear speed accuracy trade-off, which is actually a little more straightforward, so we won't need logarithms. And this one was discovered by Professor Schmidt. And I thought I'd start by just giving you a little information about Professor Schmidt's career. So Professor Dick Schmidt, he lived from 1941 to 2015, so he passed away just a few years ago. And he was a professor during a very critical time in kinesiology. More specifically, it was the transition from physical education into kinesiology. So we all know a lot about kinesiology, as most of you are either majoring or minoring in kinesiology. But preceding kinesiology was physical education. And its focus was different. And I wrote this down to kind of get it right. So physical education was mostly about learning and teaching of sports and games. So that could be physical educators, gym teachers in the education system. But it could also just be, fitness focused, say in the military or corporate settings. But it was a very different view than kinesiology, maybe more restrictive. It was a subset of physical education. Now kinesiology, I wrote this down as well to get it right, it is the scientific study of many aspects of human movement. So that could be about teaching and learning of sports and games, but there's also way more topics that fall into kinesiology. And the emphasis is really on the ology, the scientific study part. So Professor Schmidt was a professor during this era where we were transitioning, kind of growing more out of just physical education into this new realm of kinesiology, where we're still really today. One famous thing about Professor Schmidt is he founded the Journal of Motor Behavior in 1971, a very influential journal for articles on motor learning, motor control, and motor development. Professor Schmidt is also famous for authoring what I would say is the most famous motor control and learning textbook. So it's called Motor Control and Learning, a Behavioral Emphasis. And there are currently, they're on the 6th edition, if I count the pictures right here. So this is the very first edition. I've never seen this one. I found this picture on eBay. Now I'm kind of tempted to order the book. But when I was an undergraduate student, the version of the textbook we used was actually this one, the 4th edition. So that one I always remember fondly and still have it behind me and use as a resource often. But now they're on to kind of the latest edition, the 6th edition. The first version of that textbook came out in 1982, so a long time ago, and the 6th edition was 2019, and I hope inevitably that there will be a 7th edition at some point. A little more about Professor Schmidt. So after some time in kind of academia, studying motor behavior, in 1994 he joined Failure Analysis Associates, and that was an engineering and scientific consulting firm. So they would, not sure exactly what they did, but engineering and scientific consulting firms often work with insurance companies or even individuals who have had an accident or an injury to establish, okay, why did this happen? Who's at fault? Did the person just trip, or was there poor signage? Was the restaurant not kept up to standards and there was grease on the floor? And it can be all sorts of cases, and from traffic to the way our environments are built. So kind of huge area of applied motor behavior. In 2001, he actually started Human Performance Research, his own human factors consulting business. So he's kind of famous kind of within academia and also outside of academia as well. But let's talk about what he discovered, which we now call Schmidt's law, kind of posthumously in his honor. So he was actually looking to study Fitts' law, trying to address some of the concerns he had with how it had been examined, and he ended up finding his own speed-accuracy trade-off, which we now call Schmidt's law. So let's look at his task. So here's an example of the task where you start at this home position, and then we have a little target over here, and sometimes it was like a little X or a dot, or sometimes just a little line, so it's a very small target. So that's kind of the first difference, that the target doesn't really have a width like it does in Fitts' law. Now the experimenter could change the movement amplitude here. So in this experiment we're going to see that it was either 10, 20, or 30 centimeters. And if we think back to Fitts' law, amplitude was also one of the independent variables that you could change. Different trials could be, closer or further apart. Here's another difference from Fitts' law, and this is kind of the big one. So in Fitts' law, people are told just to move to the target as quickly and accurately as possible. In Schmidt's law, you were given a goal movement time. And in this original experiment, participants were told, hey, we want you to move from here to here. In one block, it would be in 140 milliseconds, and then in another 170, and then another 200. And Professor Schmidt looked at all combinations of these amplitudes and movement times. So there'd be 9 different tasks. One of them would be 10 centimeter amplitude and 140 millisecond movement time goal. And that would be, kind of one extreme. The other extreme would be, 30 centimeters with a 200 millisecond goal. But they looked at all 9 factorial combinations of those. So the participant would do a series of trials. Let's address movement time. So you might be thinking, how do you know how to move in, say, 200 milliseconds? Because we all, we have an internal sense of timing, but likely not that precise. So what would happen is you would move to the target, and at the end of the trial, the experimenter or a monitor would tell you what your movement time was. And I've done this in the lab. We'll see a video of that later. So you move to the target, and then maybe your goal is 200, and then your feedback might say, that movement time was 400. So from that, you would know, that was too slow. I need to move faster. So you move again, and so the goal is still 200, and now it says 250. So you're like, okay, great, I'm getting closer. And it actually takes most people maybe 10 trials until they get a feel for that movement time, and they can kind of accurately reproduce it throughout the rest of the block. All right, so we have a series of trials. So imagine the participant has done 10, 20-ish trials in this example. And what we're going to measure, what the dependent variable was, is what we call the variable error. Now the variable error is the standard deviation of these movement endpoints. And I'm not exactly sure why in motor behavior we call it variable error, but maybe just saying standard deviation of movement endpoints is a lot to say kind of over and over on a paper on this topic. So at some point we decided, hey, we're going to call this variable error. So when we talk about variable error in this module, just know that we're talking about the variability of your movement endpoints. So just to review, our independent variables, the ones that the experimenter controlled, were amplitude and that movement time goal. And then what do we measure from participants? That's the dependent variable, and that's variable error. So variable error, I think, is fairly intuitive. So you can think of maybe an archer shooting at a target. And in this case, we've got small variable error. The archer is very consistent. So that's, great performance. And then here, this would be medium variable error. So there's a larger spread to those arrows. So if we wanted to pick which archer is better, obviously this one is going to be the better archer because they have a smaller variable error. And then we can have, even larger variable error, and then you can imagine those arrows would be more spread out. But just remember, here we're talking about kind of your finger, and when you land, how close are you to that target across a series of trials. When we apply variable error to these independent variables, it gets a little more complicated than Fitts' law, but it's mostly intuitive. So let's walk through this. So imagine we have a participant do 2 blocks. So what would happen to their variable error when in the first block we say your movement time goal is 200 milliseconds. And then we do another block where we say, okay, now your movement time goal, you have to move faster. The movement time goal is 140 milliseconds. So if you think about doing that yourself, so we don't have proper movement time feedback, but imagine you go at a certain speed, and now we tell you have to go there faster. Okay, so same amplitude, but we've changed the movement time. So think for a second, is it easier or harder to move faster? Should be harder. If you have to move the same distance but faster, it's going to be harder. And if it's harder, your variable error should get larger. So if you're a little confused thinking kind of directly about variable error, maybe start with thinking, okay, is that task easier or harder? And if it's harder, variable error gets bigger. If it's easier, variable error gets smaller. So this is a plot from the original Schmidt's law experiment. And what we're going to focus on is this kind of first example. So we're changing movement time. So we have our 9 conditions here, and we've got the size of the variable error. So the lower the variable error, the better the performance. And we can just focus on, we could look at 10, 20, or 30 centimeters, so any amplitude, but maybe let's just think about 20 centimeters. And if you have to move in 200 milliseconds, this is the size of your variable error. It's 5 millimeters. Now, if we ask you to move faster and faster, so now at 140 milliseconds, remember that hopefully we came to the same conclusion that that's harder, and you can see what happened as variable error has increased. And we see the same pattern whether it's at 10 centimeters or 30 centimeters. So hopefully the first dependent variable here makes sense, changing the goal movement time and how that affects your variable error. Just to make that kind of crystal clear, we can look at it in this manner. So imagine you move 200 millisecond goal movement time and you've got a small variable error. Then we ask you to move faster and your variable error gets larger. We ask you to move faster again and your variable error also gets larger. For our second prediction, instead of thinking about movement time, let's think about changing movement amplitude. So what will happen to variable error when the movement amplitude increases from 10 centimeters, maybe something like this, to 30 centimeters? So movement time is the same. So imagine you make these 10 centimeter movements, and we can say you have to do in 200 milliseconds. And now you have to do a 30 centimeter movement in the same movement time. So is that going to be easier or harder? So hopefully we're on the same page here. Well, it's going to be a larger amplitude, that's harder. And if it's harder, your variable error should increase. Hopefully we're all saying increase. But let's look at the data, and we will see that pattern. So it doesn't matter whether we look at 140, 170, or 200, we see that same pattern, but we can focus on maybe these 200 millisecond movements here. And if we ask you to move 10 centimeters, you have a 3.5 millimeter variable error, so that's good, small variable error, great performance. And then we ask you to move 20 and then 30 centimeters in the same movement time, so all these are 200 milliseconds, and you can see variable error increases. So as the task gets harder, again, variable error increases. And just to show it in the same secondary way we looked at before, so 10 centimeters, you've got a small variable error. Now we ask to move 20 centimeters, that variable error will get larger, and 30 centimeters, the variable error is even larger. So Schmidt's law, similar to Fitts' law, is logical. It makes sense. And I think in Fitts' law and Schmidt's law, either of those I could explain to my grandmother and she would say, sure. If the task is harder, you're going to have larger variable error. That's rather intuitive. And it makes sense, but that's not why Schmidt's law is a famous law. We're going to see that the relationship between speed, or your movement velocity, which we'll get to in just a moment, and accuracy, your variable error, has a linear relationship. And that's kind of the more exciting, interesting part to Schmidt's law. Because just the idea that we trade off speed and accuracy, yeah, that's somewhat obvious, or hopefully makes sense after a quick explanation. So let's get to the kind of the real interesting aspects to Schmidt's law. And the first genius was his ability to quantify the difficulty of each movement. So sure, we can say that as we decrease movement time, that's harder. And as we increase amplitude, that's harder. That makes sense qualitatively, but we want to quantify difficulty, right? We are quantitative scientists. We're going to need some numbers. So Schmidt suggested that, well, maybe what we can do to quantify the difficulty is we can look at the goal amplitude and divide by the goal movement time. And those are our two independent variables. Now amplitude, remember, is a distance, and movement time is a time or a change in time. So if I say, hey, distance over time or distance over change in time, that is velocity. So there is some logic to this, that we're not just picking two variables at random and dividing them. Well, we're taking our dependent variables, and that division, the idea is that we're estimating the velocity of our movement. And that's very helpful because now we have a single number to quantify the difficulty of every movement condition. More recently, in some research we'll talk about that I've been doing, instead of estimating the velocity of the movement by taking the amplitude divided by the movement time, we can use motion capture to track your movements and actually measure your velocity throughout and then calculate the average velocity of each movement. Bit of a side. Okay, let's now, instead of plotting movement time on one axis, in the legend, and amplitude on one axis, what we're going to do is we're going to calculate these velocities for each condition, and on the x-axis we'll have velocity, and the y-axis we'll still have our variable error. Ooh, great. So I forgot to mention two examples here. So this is the condition with the best performance, so it's the easiest condition. And if we think of what's the easiest condition, well, the shortest amplitude, 10 centimeters, and you have the longest movement time, 200 seconds. Sorry, I got confused. 200 milliseconds, but I've converted it to seconds here, so 0.2 seconds. So here, basically the difficulty of this condition is 50, and we're thinking about that in terms of a velocity. We expect the average velocity of your movement to be about 50 centimeters a second. Now over here, this is our most difficult condition, and we see the largest variable error. So the difficulty in this case is 214, and just like Fitts' law, the higher the difficulty, the harder the condition. And here you had to move 30 centimeters, that's the biggest distance in this experiment, and you have to do in the shortest time, 140 milliseconds or 0.14 seconds. So here we're predicting that your mean velocity of your movements is much higher. It's 214 centimeters a second, and that's going to result in a much higher variable error. All right, here are the data replotted. So now on the x-axis, we can think of this as the velocity of your movement or the difficulty of the conditions that we're giving you. And what we see is that, yes, there's this nice linear relationship between your speed or velocity and your accuracy measured by variable error. Here are those two conditions I pointed out on the last graph. So remember, the easiest one with the lowest variable error has a mean velocity of 50 and a variable error of 3.5. And as the task gets harder and harder and harder until the hardest condition, we now have a mean velocity of about 200 centimeters a second and a variable error of about 9. So this was the second genius of Schmidt's law, and that was finding this linear relationship between speed and accuracy. And that's not given. We saw in Fitts' law, for example, that there was a logarithmic relationship. So if anything, maybe you would have guessed that, hey, there'll be a logarithmic relationship here, because that's what we do in Fitts' task. But in this case, it's linear. And remember, there are very few laws of human movement. So yes, it's not perfect, right? All these points are not exactly on the line, but it's surprisingly accurate, and that's why we consider it a law of human movement. We can calculate Schmidt's law by finding the equation of this line. And this kind of reproduces exactly what we did with Fitts' law. So we start with y equals mx plus b. For x and y, remember, we're not putting in values. What we're going to do is we're going to put in the labels of our axes. So y is variable air, sometimes abbreviated VE, and x, this is our a over mt. So we can put those in, and then we would need to calculate the slope. So we could calculate the slope of this line. We could calculate the y-intercept, which if I predicted here is maybe around 2 or 2.5. We'd put those numbers in, and that would give us Schmidt's law for these data. Let's compare Fitts' law to Schmidt's law to each other. And we'll get to the dependent and independent variables in just a moment. But the first thing I want to mention is that most of our movements in daily life probably fall within the Fitts' law paradigm. So remember, in Fitts' law, we tell you to move to a target as quickly and accurately as possible. And if I want to pick up this Lego figure, then I'm probably, even though I don't have to move to as quickly and accurately as possible, in daily life, we want to be efficient. I want to pick this up and move on with life. So I'm probably moving to it in a way where I'm trying to be quick and accurate. It's probably fairly similar to official Fitts' law task instructions. So most of our movements in daily life, unless I guess you're being super lethargic, or let's say this was very, very delicate, then I might not want to move as fast and accurate as possible. I might really want to move as accurate as possible. But I think lots of times when we move, we're balancing speed and accuracy, which is kind of like the Fitts' law instructions. So lots of movements in daily life can fall into this Fitts task realm. Now Schmidt's law, they're not the most common movements. That's Fitts' law. But Schmidt's law, we do make movements like this, and the best examples I can think of are, think of a musician. So if you're a drummer and you need to hit the drum on the beat, or I guess you are the one making the beat, you need to keep a set tempo, well, all of a sudden you need to do that movement with a goal movement time, specifically the tempo of the song. Or think of a dancer. So if you're dancing with music, then you have these movement time goals. You need to move from one position to another in your artistic dance with the beat. So Schmidt's law, although it's not maybe how we move in most daily tasks, it does occur when we move. There are examples of movement time goals, and that would be like music and dancing. Let's get back to our independent and dependent variables. So to review, in Schmidt's law, the experimenter controls two things: the target amplitude and the movement time. Now what do we measure? That's the dependent variable, and we measure the variable error. Now that variable error, the size or say the width of your movement endpoints, is kind of like a target width. Now remember, there's not actually a target width. There's often just a dot or a little cross that you're aiming for. But variable error and target width, they're related. They're in the same realm. Let's go to Fitts' law. So Fitts' law, the independent variables are amplitude and target width. Now note that in both of these tasks, target amplitude is an independent variable. So it's like exactly the same. But here, target width is an independent variable. And in Schmidt's law, well, the closest thing to target width is variable error, and that's a dependent variable. So we kind of have two changes. Target width, variable error, not identical. And in Fitts' law, it's an independent variable, and in Schmidt's law, it's a dependent variable. What do we measure in Fitts' law? Well, we measure your movement time. What's your average movement time? So the dependent variable is movement time. And here we see another change. So in Fitts' law, movement time is a dependent variable, In Schmidt's law, it's an independent variable. So what I'm trying to show here is that both tasks kind of have the same three variables, if we want to think that target width and variable error are kind of the same, but we've shuffled which ones are independent and dependent variables. So here we have, this is the graph back to the original Fitts experiment, and here we have our original Schmidt's experiment. And the key difference between them is that, Schmidt's law has this linear relationship, so we see a nice straight line without any logarithm. For Fitts' law, to get a straight looking line, remember we had to apply a logarithmic transformation, and that's why we say Fitts' law is a logarithmic speed-accuracy trade-off, and Schmidt's law is a linear speed-accuracy trade-off. And one thing researchers were interested in when Schmidt's law was discovered is, well, why is one linear and the other logarithmic? And one of the initial suggestions was, well, maybe it's because we've been testing different movement times. So if we look over here at Fitts' law, the movement times typically range from 200 to 750 milliseconds. So 0.2 seconds or 200 milliseconds up to 750 milliseconds. And those are kind of moderate movement times, if you will. When we look at the original Schmidt's experiment, well, the movement times were much shorter. So they were range from 140 to 200. So I guess both experiments of 200, but generally we can say that Schmidt's law, there were shorter movement times, and Fitts' law, there were longer movement times. So there is this question of, well, is one linear and one logarithmic because we didn't fairly compare them? With Schmidt's law, people were moving very fast, and with Fitts' law, people were moving generally slower. And maybe that's what caused the difference. So we're going to look at one of the experiments that tried to determine whether that was the critical difference between these tasks, just the kind of average movement times that participants are moving in. This is an experiment by Carlton, very well-designed experiment. I really enjoy this one. So what he did, it's fairly straightforward. Participants would come in on the first day, they just did one condition of a Schmidt's task. So for the participant, this was fairly straightforward. You don't have to do 9 conditions, just one condition. So there was this set target amplitude. I forget exactly what it is, but let's run with that it was 20 centimeters. And it's always going to be the same. So you're moving 20 centimeters to this very small target. And because we don't want to have people moving fast like they did in the original Schmidt's experiment, we're going to ask them to move at kind of an average movement time for Fitts' law. And Carlton decided he would use 400 milliseconds. So participants here are told to land as close as possible to the target with a goal movement time of 400 milliseconds. And they would do a series of trials, and then Carlton could then measure their variable error, or the standard deviation of their movement endpoints. Now, Carlton, so they did that one condition, they left, he would analyze their data, and he would calculate their variable error. And then what he did is he actually made a physical disk out of metal that was exactly the size of their variable error. And nowadays we could probably do that kind of instantaneously with a computer, but because Carlton constructed this disk, participants went away, he worked on this maybe in the evening overnight, and then they would come back on the next day when he had this disk prepared. So day 1, participants do Schmidt's task. How did they do? Well, remember that on your early practice performance, we give you feedback. So we'd say, oh, that trial was 350. Oh, that one was 450. So participants would know, oh, I'm too fast, I'm too slow. And after a few trials, you would get good at hitting this goal movement time. So what he found is that participants, yes, they followed instructions, and the average movement time was very close to the required 400 milliseconds. So all this says is that, yes, participants are doing this task properly. All right. Now, day 2, participants came back, and now they're going to do Fitts' task. It's the same exact amplitude as day 1. I suggested 20 centimeters. And now they're given Fitts instructions. So now they need to move to the target as quickly and as accurately as possible. And we have a target with a target width. And the width of this target is their variable error from the previous day. Now Carleton didn't tell them that. He maybe could have. I don't think it would make a difference. But to be unbiased and fair about how we're running this experiment, we just say, hey, now you're doing a slightly different task. And hey, check out, here's the target. But the clever thing is that the target width matches the variable error from day one. The idea here is this is how to equate the Fitz task to the Schmidt's task as closely as possible. We want to compare apples to apples, not apples to oranges. Now we can't change the independent and dependent variables. Those have to be different, otherwise it's not Fitz task and Schmidt's task. But to make them as comparable as possible, the target width in Fitz task is the variable error from Schmidt's task. So kind of a clever way to compare these things. So now the participants go ahead, they do Fitz task, and Carleton was at first mostly interested in their movement time. And he had two hypotheses. He said, okay, if Fitz law and Schmidt's law are really the same law, and we just hadn't been fairly comparing them before, but now that we're equating them apples to apples as close as possible, if they are one and the same law, then movement time here should still be 400 milliseconds. Because when we told you to move in 400 milliseconds, you had this variable error. So if we give it back to you and say move as quickly and accurately as possible, your movement time should still be 400 milliseconds. Alternatively, if Fitz law and Schmidt's law are different laws, if one instructions cause you to move with this linear speed accuracy trade-off and the others cause a logarithmic trade-off, then movement time should not be the same. In this second day, when you do Fitz tasks, movement time should not be 400 milliseconds. So for the first critical question here from Carleton is, on day 2, is the movement time 400 milliseconds? Again, if so, Fitz and Schmidt's are the same law, and if not, they must be unique different laws. So here's day 2, and to add some excitement, I've put in some fireworks here because the number didn't kind of convey the significance of the results. So you can see here, or what they found, is that movement time was not the same on day 2. So you're much faster in Schmidt's task. You have this shorter movement time than in Schmidt's task. And that's them trying to equate as many differences as possible between these two tasks. So those results support hypothesis 2. Fitz law and Schmidt's law must be two different laws. And that's why we've got two modules for these two laws, and we still believe even today that yes, they are in fact unique ways that we trade off speed and accuracy. So Carleton's experiment went a step further. He also looked at how participants move from the start to the target to try to infer how they're moving. Are they using online corrections? Are they using closed loop control or not? And to do that, he relied on motion capture. Imagine we have a little light or a marker on your finger, and as you move, a camera records exactly how you move. And then once we have that data, we analyze your trajectory. So we call that trajectory analysis. But first, to just learn a little more about motion capture, let's check out this video. The link's in the description. And this shows motion capture technology that's mostly marketed towards, athletes and coaches and those working with athletes. So, digitizing their movements and then understanding how people move and how to change their movement to, say, be more efficient or reduce risk of injury. So take a moment and check out this video and come back and we'll talk more about examples of motion capture before getting back to Carleton's study. The other place you've likely seen motion capture is kind of the entertainment industry. So you can think movies, motion capture is more and more common for digitizing an actor's movements into a film. So that could be Mark Ruffalo here playing the Hulk, right? So he played both versions of the character, but when he's the green big Hulk, obviously he's got to look a lot different. So they do motion capture of his body movements and even his face to digitize those expressions into the film. And that's what makes it look very realistic, because the animation, the digitization, comes from his real human movements. They've gotten even better doing this with faces. So this is from one of the, the Planet of the Apes films. And all these little dots, there'd be motion capture cameras tracking them so they can get these very realistic human expressions into these digitized characters. And if you go back, probably maybe even only 20 years, they weren't able to digitize the face this well. So maybe the character movements were digitized, but the facial movements still looked a bit artificial. And probably 20 years from now, they'll move on from, let's say maybe there's 100 markers on the face, maybe they'll have 1,000, or maybe they'll be able to track the face with markerless motion capture, every millimeter, and then maybe they can digitize, even like the tiniest hairs and wrinkles from the actor into the film. The other place this is used a lot is in video games, especially sports video games. So the movements need to look realistic, otherwise, it looks off. So the way they do this is they have, real athletes perform the movements in these giant motion capture studios. This is one of EA's sports studios up in Canada, actually outside of Vancouver. They have this giant facility, and here they have their basketball court down. They've got basketball players, and they'll even bring in actual athletes to capture their exact movements. So if we think LeBron James or Steph Curry, if we compare their layups, they're different. And you can see that, and if they use the same layup animation for every person in the NBA, it wouldn't look right. So they won't necessarily bring in every player, but they will bring in especially famous players to do kind of their signature moves so that in the game it looks like it would on the court. And this facility is really neat. They've got artificial ice they can put down to capture, skating movements, because EA does a whole variety of sports games. Okay, so that's motion capture. Let's bring this back to motion capture used in the lab for research. And this is quite common in motor control research, also in biomechanics. And here at kinesiology, there's a motion capture set up in my lab. So you can see we have a bunch of cameras, and they are recording lights that we put onto the participants. So this is me from several years ago. And in this experiment, you're picking up these Duplo blocks and moving them. And we had a light on the, can't really see in the picture, but there's one on the thumb, one on the index finger, and one on the wrist. And that would allow us to capture exactly how you move, grasp, and move these blocks. Here's an example from Schmidt's law from just this past spring semester. And here I'm holding a pen. So instead of your finger, sometimes we hold a pen or a stylus, because it has a pressure sensitive tip, so we can tell when you're pressed and when you're moving. That allows us to estimate your movement time. So these are the lights. They're on now. The cameras, they're kind of around. You can't see them in the picture, but they're tracking these lights so we can know exactly how you move to the targets. And here we'll see I'll start at the home position over here. And this block I've been told to move to this middle target. It's a very small dot right there. And my goal movement time, I think, was 225 milliseconds. And after each trial, the monitor will give me feedback on how I did. And you'll see just a couple trials here. So here's the feedback. So next trial, so it was 229. That's close. I'm trying to move in 225, so that's pretty good. 220, and I've done this before, so these aren't my warm-up trials. I'm already good at kind of hitting that movement time. But that's Schmidt's task in the lab, and that's how one way we can do motion capture. And we'll actually come back to these data in a moment. But let's talk about how Carleton looked at the trajectories. And one thing that's been shown in many studies is that we can look at what the trajectories look like and make inferences about whether you used online control or not. So let's start here. So these type of movements, we consider them to be open loop. So you're not using closed loop control, you're not using these online corrections. So here's the displacement or the position. The participant moves from a home position to the target. This is time. So that's displacement or position. We can differentiate this to calculate your velocity. And when you move in open loop control, we see these smooth velocity profiles. And typically maximum velocity is near the middle of the movement. We call this a bell-shaped velocity profile. So when we see a smooth trajectory, we say, hey, that's probably open loop control, and you're not making online corrections during the movement. Now, what does it look like when you make online corrections? Well, the short answer is jagged trajectories. So here's an example where the participant moved. Guess they moved too far, so then they came back. They realized, oh, that's not far enough, so they move a little further and they come back again. So those are multiple corrections, and that's probably not the typical amount of corrections you make. And that's a lot of corrections for a single movement. But if we differentiate this to get velocity, we can see, look how jagged that velocity is. And if we look at maximum velocity, it's no longer in the middle. It's not this single bell-shaped velocity profile we saw over here. We see jagged velocity profiles. This is maybe a more realistic correction where the participant moves, and then maybe from visual or proprioceptive information, they've realized, oh, I'm not going to hit the target, so they re-accelerate to move a little further. When we look at the velocity profile, instead of just this one peak in velocity, we see two. So again, jagged velocity profiles with maybe one or more corrections suggest closed loop control. So Carlton looked at the trajectories in his two conditions, and he wanted to see, were they smooth or were they jagged? If they're smooth, it suggests open loop control, and if they're jagged, it suggests closed loop control. In Carlton's article, he does show some trajectories, but they're kind of averages, and his motion capture is maybe not as good as we have nowadays. So I've replaced this with my own data from Schmidt's task, the video we saw, and then a previous experiment where we did Fitt's task. And these are roughly similar conditions, but they're not as well as equated as Carlton because these are actually two different experiments. But if we look at Fitt's task, and these are the velocity profiles, you can see they're jagged, right? There's a lot of corrections going on. So these jagged trajectories suggest that in Fitt's task, you're using closed loop control. And this is what Carlton expected for Fitt's task. Now for Schmidt's task, from our data and what Carlton reported, the trajectories were fairly smooth, and Carlton concluded that these smooth trajectories must be caused by open loop control, or the lack of any online corrections. You prepare your movement at the start. So if you're the participant, you say, okay, I'm going to move there in 400 milliseconds, and you do your movement, and even if you realize, oh, I'm going to miss too far, too short, you don't do online corrections. And maybe we don't make corrections because if you did make this online correction, yes, you'd improve your accuracy, but you're going to throw off your movement time. And in Schmidt's task, the movement time, the temporal precision, is of critical importance. You're really trying to hit that movement time goal. So maybe you don't want to make online corrections because it will throw off your movement's timing. So let's just talk about Carlton's conclusions here. So he said, it's not that movement time is different that causes these linear and logarithmic trade-offs, because Carlton equated those and they still had different movement times. The critical difference, as I kind of suggested on the previous slide, is that temporal precision. So as soon as we tell you to hit a movement time goal, your brain seems to say, okay, I'm going to move in open loop control because if I do any corrections, I'm going to throw off that movement time. So we bring this back to musician. So if they're like, okay, I need to hit that drum, it's critical that they hit it at the right time, right? Otherwise, they're gonna throw off the whole band by having the wrong timing. So they're not going to worry too much exactly where they hit on the drum, and it's good that the drum is large. If it were tiny, then that would be problematic because they would have to make these online corrections, throwing off their movement timing. So when we have these conditions where you need to hit a movement time, your brain seems to switch off using closed loop control. You say, okay, I better not do that because I need to be temporally precise. So in the end, Carlton concluded that, well, in Fitt's law, we use closed loop control, and Schmidt's law, we don't. We use open loop control. And when we use open loop control for whatever reason, that causes a linear speed accuracy trade-off. And when we start to invoke online corrections and closed loop control, that results in a logarithmic speed accuracy trade-off. So they're not one and the same laws, and we know a little more about why they're different. So I've done a couple of experiments on Schmidt's law, so I just want to tell you about one of those and get to some of the nuance, why and how do we move differently in Schmidt's law. So here's the experiment, and it's very much like that video of me you saw earlier, except in this original experiment we had 6 targets, so there were 6 conditions. This first one was the easiest because it has the shortest amplitude and the longest movement time. And here we can see kind of the difficulty or our predicted average velocity. And we could also measure their actual mean velocity because we had motion capture data. The hardest condition was the furthest target, so it was 30 centimeters or 300 millimeters away, and you had a very short movement time goal of 194 milliseconds. And this one was actually fairly hard. Some participants could do it, some couldn't. I'm sure if we gave people more practice, everyone could, but this condition was kind of pushing the limits of people's abilities on their first day coming to the lab. So let's talk about kinematics for a second. So here we have position, and this is from the actual results. Here you can see a participant starting at the home position and moving to the target. And in this case, they did the movement in about, well, we'll say 270 milliseconds. So it's kind of one of the easier movements, moving out to the target. We can differentiate these data to get the velocity profiles. And here you can see that's kind of a nice bell-shaped velocity profile, pretty smooth. So we're still seeing these smooth velocity profiles. And we can differentiate velocity again to get acceleration. And if you're in biomechanics, you might already know a lot about that. But we won't worry about the math behind it for now. So here's your acceleration profile. So you get this burst in acceleration, and then you got to slow down your movement, so we get this negative acceleration here. And I'm just showing you this because on the next plot, what we'll see is they look at the movement throughout time. But instead of using time in milliseconds like we see here, they look at time in terms of when do the kinematic landmarks occur. And the first kinematic landmark, the first one, the easiest one to find in a movement, is maximum acceleration. That's just a really easy point to find. Now the next time point they pull out is maximum velocity, and maximum velocity is also when your acceleration crosses 0. And their last time point is minimum acceleration. That's a very easy kinematic landmark to find in every movement. So we'll see those 3 kinematic landmarks, and just know that we're looking at the movement kind of from early on until the end. All right, here's a plot, and this one's going to be important. So we have those kinematic landmarks down here. So we don't have the very start of the movement, but we've got maximum acceleration, and then later is maximum velocity, and this time point is between those 2 landmarks. And then later on we have minimum acceleration, so that's near the end of the movement, and then they had a couple of later landmarks here. What we're measuring here on the y-axis is the variability of your movement. So imagine you're going to do a bunch of trials where you move to the same target in, say, the same movement time. And what we can do is we can look at where you are in space at maximum velocity. And we're not robots, right? So every trial you're not exactly in the same spot like a robot would be, but maybe one trial you're here, one trial you're here, a little shorter, a little further. So if you think of where you are at maximum velocity, there's going to be this variability to it. And you can think of it like variable error, but it's just not at the movement termination or the endpoint, it's during the middle of your movement. And we can capture that variability throughout the whole movement. And what we see if we look at this pattern in black, and this is when you move with vision available, is that your variability at the start is very small because you're in one spot. And then the further you go, the bigger the variability is until kind of till around minimum acceleration. We've reached our maximum variability, and then we see a decrease in variability at movement termination. And the reason for this is variability tends to increase as we move because we're moving with open loop control. Remember, all movements start in open loop control. And we're not robots, so every trial is a little different, so we get this increase in variability. That's problematic because we need to hit a target. So if to hit a target, we're going to have to decrease that variability to be small or at least the size of the target. So once there's been enough time for closed loop control, it kicks in, we start to make these corrections that decrease our spatial variability, allowing us to hit the target. So when we see this decrease in spatial variability or variable error, we infer that closed loop control has kicked in. So you can think of this like a typical Fitts law movement where you have vision. Now lots of experiments to look at reduced closed loop control. They have you move, but as soon as you start to move, you're wearing these spectacles that close. And you now have no vision during movement execution. So that's this condition here. It also has this increase in variability. So this is also open loop control. But without vision, you can't do as much closed loop control. You still have the proprioceptive information of your hand, but that's not super helpful because we're aiming for a target, we can't feel the target. It'd be ideal if we could see our finger and see our target and we can use closed loop control. So when we get rid of vision during movement execution, what we see is this increase in spatial variability, which we also saw in this other condition, but then we see it plateau. We see it increase and it kind of gets to a maximum amount and then it just persists. It doesn't get smaller to allow us to home in on the target with closed loop control. Now what Carlton was wondering, and what I looked at further, is okay, well, Fitts law, this is what we expect. We expect this use of closed loop control. Now Carlton, in his results, said that, okay, well, Schmidt's law, this is likely what we're seeing. We see an increase and then a plateau, because remember, Carlton said that Schmidt's law was done in open loop control. Now Carlton measured whether you were using open loop or closed loop control just by visually examining trajectories for smoothness or jagged velocity profiles, which is still used today. We typically now quantify it a little more scientifically, but the experiment I ran, we wanted to use kind of a more modern way of differentiating closed loop control from open loop control by looking at spatial variability throughout the movement. And this really requires kind of sophisticated motion capture technology, something far more prevalent now than in the 90s when Carlton did his work. So what did I find? So here's the experiment. You're moving to these 6 different targets, and we're looking at your spatial variability. Here I've called it variable error. So think of it as your spatial variability throughout your movement. And the red condition here, this is the spatial variability for the first target, and then the green is the second, third, fourth, fifth, and sixth. So that hardest target, you see this huge increase in spatial variability, and that's because you're moving faster, and the faster you move, the less accurate you are, so a speed accuracy trade-off. And in this short condition, so you've got a lower velocity because you don't have to move very far, and you can see there's this increase in spatial variability. The neat thing though, so all of them show what we predicted. They start with open loop control, but the surprising result is that they all decrease in the latter half of the movement. And really, from what Carlton and others had said, I didn't really expect this. I thought spatial variability would increase and then plateau, very similar to what we've seen previously when people move without vision. But that wasn't the case. In every condition, we see closed loop control. So what do we conclude from this? So surprisingly, movements in Schmidt's task are not completely open loop as suggested by Carlton and others. They do involve closed loop control. However, there's likely far less closed loop control in Schmidt's task compared to Fitts' task. And so let me read it the same way it's written here. There's likely more closed loop control in Fitts' task compared to Schmidt's task. So if we go back to these trajectories, these are jagged, very obvious closed loop control. Schmidt's tasks, they're not very jagged, but when we look at spatial variability, we do see evidence of some closed loop control. So what we think we're seeing here, and we're running some follow-up experiments, is that there seems to be a difference in the amount of closed loop control. Fitts' law, there's a lot, which is very obvious from these jagged trajectories. Schmidt's law, initially you would say, oh, it looks like open loop control, but when we look at the spatial variable, no, there is some closed loop control, but probably not nearly as much as there is in Fitts' task, causing these huge jagged peaks to their trajectories. So it looks like it's more about not yes or no to closed loop control as concluded by Carlton, but more closed loop control in Fitts' task and less closed loop control in Schmidt's task. And in some experiments, we're in the middle of processing, so I don't want to kind of make two conclusions too soon, but we're trying to delve into, well, what type of closed loop control? And it seems like the type of closed loop control is different between these. That kind of goes beyond what we've talked about today. So as a quick wrap up to these two modules, we have two speed accuracy trade-off. We've got Fitts' law, it's a logarithmic trade-off, and it applies to kind of our typical movements where we're trying to be quick and accurate. And then Schmidt's law, it's not the most common type of trade-off, it's linear, but we do see it when you have to hit a movement time goal, and that could be the case for a dancer, a musician, and for athletes, this also applies as well. If you are a baseball batter, you need to swing the bat, but the bat needs to hit the ball. There's a timing requirement. So in that case, Schmidt's law might also apply to those sorts of interception movements, so catching a football, baseball, things like that. So take a look at the practice questions, and then when you're ready and feel confident, good luck with the test.